Unambiguous and simple language.
Good morning, Professor Vasnawala.
Good morning, Professor Dar.
Thank you for accepting our invitation for this lecture. Thank you very much, sir.
It's my pleasure, sir.
Thank you, sir. Thank you, sir. We'll start exactly at 11:30.
Okay, then I'll start at 11:30.
Yes, just we will give you our introduction first, then we'll start. You will start. You will share your presentation.
Okay.
Thanks.
Good morning, everyone, and thank you for joining in again. The people who don't know, my name is Sakiba Nabi, and I am moderating the session today. Our second session for the day will be by Dr. Sandeep A. Vasanwala. He will share his knowledge with us on neural approaches for the preliminary design of double-layer space grid structures. Dr. Sandeep A. Vasanwala is a professor in the Civil Engineering Department of SPNIT Surat. The major areas of his research include neural network applications in structural engineering, neural application for preliminary design of structure and space structures, etc. He did his PhD from SVNIT Surat and since then has contributed immensely to the field of structural engineering and as a whole to civil engineering. It is an immense pleasure to have him with us today. And without further ado, I would like to invite Dr. Sandeep A. Vasanwala to start the session. Please, sir.
Thank you, ma'am, for your kind introduction. Good morning to all participants. Now, today, I am going to discuss some of my research activities in SVNIT, that is neural approaches for the preliminary design of double-layer space grid structures. This is a kind of structures which is horizontal structures when you need large unobstructed space, like in case of sports arenas, exhibition pavilions, airport hangars, swimming pools, industrial exhibitions, halls, and so on. My approach today will be to brief you about double layer space grid structures, then what we did here as far as the geometrical configuration efficiency, which leads to minimum weight design, which is a generally economical design in case of such a huge steel structures. And then I'll show you, demonstrate how neural approaches, artificial neural network, that is multi-layer perceptron, feed-forward multi-layer, feed-forward perceptron, and radial basis function. I'll explain what is the difference between these two and why we have considered this two neural approaches for preliminary design of double layer space grid structures. So my flow presentation will be, I'll give a brief introduction of the double layer space grid structures. Then I'll discuss something about the geometrical configuration efficiency. And then we generate the huge database with which we can train the network. And then I'll explain about ins and outs of application part of artificial neural network, that is multi-layer feed-forward network and radial basis function. It is also a multi-layer feed-forward network, backpropagation net and radial basis function. I will not indulge more in mathematics because this is not the platform at which I should explain you all those things. But my main intention is to show you what neural network can do in the field of structural engineering. See, the space frame structures are a typical examples of skeletal frameworks consisting of a large number of simple, modular, prefabricated units, often of standard size and shape. They are interconnected to a light but very rigid two-dimensional structures. One of the most important developments in the field of space structures in recent years has been the evolution of various types of double layer grids. There are other kinds of space structures like cell, dome, grid, but this is aesthetically very very impressive beauty, and it is very simple to construct than the other forms of space structures. The engineers appreciated great rigidity and stiffness of the structure, which is required because of a large unobstructed space, so the deflection serviceability is the rather governing criteria. And second is that the exceptional ability to resist large concentrated loads or unsymmetrical loading. The reason is that when I'll show you, if you look at the geometrical configuration, there are thousands of elements which are interconnected with each other. So whether you put load unsymmetrical on that geometry or very concentrated load on only some part, rapidly this will be transferred to a number of what you can say simple connecting elements, and that is what is engineers appreciate. Architects generally appreciate the visual beauty. It looks very beautiful and impressive simplicity. It is very simple to construct it. This is double layer space grid structures, which is having two plane grids, one at the bottom and one at the top, but they are not necessarily of identical layout. They are parallel to each other and they are interconnected by either vertical or inclined web members. The resulting structure is thus a typical example of a two-dimensional system in which any external loads are rapidly distributed among numerous bars. These are some of the examples of double layer space grid structures. Say sports arenas, exhibition pavilion, as I told you, assembly halls, swimming pools, transportation terminals, airport hangars, shopping arcades, and industrial building. These are the main areas where you can go for the double layer space grid using similar tubular double layer grids have been built over sports centers in Germany, France, Romania, Czechoslovakia, and Poland. So generally, This has started in Europe in around 1960s. Now, what is the economic issue? So the selection of proper grid layout, geometrical configuration, and the member sizes requires to start the first cycle of analysis is of utmost importance for obtaining a rational and economical design. The weights arrived at with the preliminary design form the basis for competitive bidding and are often decisive in winning the contract. Now, this is one of the most important observation where neural network fits, because neural network is a kind of tool which you should apply where you come across difficulty in solving the problem traditionally, in a traditional way. It is not that neural network can do the things which a traditional way cannot do. It is not like that. But some of the things which are very tedious to do, which are error prone, which consumes a lot of time, for such scenarios, neural network can give a very viable alternative tool and solve your problem with less complexity and fast. See, generally what happens that when you wanted to bid for is such structures, generally such structures are mostly government structures. A huge cost is being involved. Now, when you bid the contract, you have to anticipate what are the tonnages. This is one of the single most influencing parameter, weight, tonnages of the space grid structures which you encounter when you execute the bid. If you fail in do so properly, then it will not put you in a competitive bidding scenario. But when you want to bid with a specific cost, means you have to predict tonnages, means you have to predict tonnages in connection with the proper design. Because here, rather than strength, deflection is a governing criteria. This is a very, very huge horizontal spread structures where deflection play a very critical role. So you have to predict the weight at preliminary stage, but keep in mind that it should satisfy the serviceability. Otherwise, there is no sense in predicting that weight and then ultimately the cost. But you don't have much time when you bid the contract. So it's only your gut feelings or your expertise with which, or if you have some tool by which you can quickly do the computations at preliminary or conceptual design stage, because very less information is available at the preliminary design stage. It is a stage of the design where the uncertainty degree is very high. So there the neural network is one of the tools which comes to your aid. So that is what is the whole, what you can say, concept of deciding the neural tool for predicting weight and deflection at the preliminary design stage. Then the space frame competitiveness to other structural system depends much on the final weight. Why? Because the cost depends on that, and the relative stiffness, which in turn depends on the decision taken at the preliminary design stage. So first, let us discuss geometrical configuration efficiency. These are the parameters on which it depends, like type of grid, span length, span to depth ratio, depth to module size ratio, module size, support type, and aspect ratio. Now, say these are, if you see here, this is module size, this is depth, this is span, this is support condition, this is aspect ratio, and so on. So these are the, we work on 5 different grid configuration. This is, I have depicted it over here. General arrangement, it will look like this. Top chord is square, bottom chord is square, and this is bracing. So this is termed as square on square grid. So when you put square on square grid, it looks like this. That's a general arrangement. Then it is square on larger square grid. Then it is square on diagonal grid. Then it is diagonal and square grid. And then this is diagonal and diagonal grid. These are the 5 grid patterns, and these are the 4 support conditions on which we work. This is all edge nodes are supported. Alternate edge nodes are supported. Then 3 corner nodes and 1 at the center of each edge node is connected, and only 3 corner nodes are connected. These are the design parameters, like span length, we consider 24, 30, 36, 42. Span to depth ratio, L by 12 to L by 20, and L by 16 to L by 24. I am not going into more detail. Otherwise, for every parameter, we did extensive R&D. What actual people provided, what are the other connected to this, what are the other parameters which researcher found give you cost-effective solution that we have selected from the different researcher works. So span to depth ratio for 24 meter is this, and for 30, 36 and 42 meter is this. Grid aspect ratio for 24 meter, for 30 meter, and for 36 and 42 meter. And the support arrangements are H1, H2, H2, and H4 I have shown you. Such 700 models, analytical models we have generated. The dead load we consider 0.9 kN per meter square, live load 0.75, basic wind speed for Surat we consider 44 meter per second, and the element temperature, because it is in open air, so the temperature we consider the 20 degree centigrade. That's a gradient, 20 degree centigrade gradient we have considered for all the patterns of the structures. So what we did is that these 700 models, different 700 models we analyze for cost-effective solution. How we do analysis, that I am showing you later on. The material properties we consider are, this is a steel structure, tubular steel structure. So modulus of elasticity, Poisson ratio, thermal coefficient, and weight density. And the specification of tubes, generally it is YST 310 grade, 1161, 1998 IS with yield stress of 310 megapascal. The node connectors are marrow connectors. This is the widely used connector for double layer space grid structures. We constructed few space grid structures on our campus SVNIT itself using the marrow joint. Now the design code, which I consider at the time of research, because this research carried out between 2005 and 2007. So it was not 2007 code, but it is 1998 code. This is a typical marrow connection. The major innovation in page frame came about when Dr. Max Manzinghausen introduced his marrow system. He is a German person in 1943. The marrow connector was originally developed for double layer space grid structure, but you can use it for all domes kind of structure also, tensegrity structures also. Now see what I did, how I did analysis and design of the 700 different models. So generally, I did modeling. That is the geometry I generate in Formex. Formen is the language. I'll show you one simple code also. This Formex is University of Plymouth. They developed this. It's a very simple language, and it is specifically developed for generating models of space structures where thousands of elements are there, and it is difficult to generate the model even by using AutoCAD because 1,000 elements are there, and nowadays, no doubt, after 13, 14 years, you can directly develop it either in AutoCAD or Midas Gen also. But still, it is not that error-proof and speed with which you can develop it in Formin. I'll show you one simple code also. So what I did is we develop it in form. We have written Formin code. Then automatically the model will be generated. That model we export into AutoCAD. Then we, through AutoCAD, we import it to Midas Gen, which is integrated analysis and design software package, one of the best package globally available, like ETAP and SAP. It is parallel to ETAP and SAP. And in graphical user interface is much better than even ETAP and SAP. Then I did modeling in Midas Gen. So material properties and section properties and boundary condition you give. Then you define load cases and load combinations, give loading, then do the static analysis. I did static analysis. What I did is that there are 3 layers: bottom layer, top layer, and web, intermediate layer. Thousands of elements are there in each layer. You cannot design each and every element with different geometrical properties. Otherwise, it will be very uneconomical. It is error prone. It is very time consuming even to construct it. Nobody can construct it like that. So what you have to do is that you have to do member grouping. So again, many researchers has worked a lot that each group like bottom, each layer like bottom, top, intermediate, in how many group you should split. So starting from what you can say total group 3, that is one element in each layer, one cross-sectional element in each layer, geometry, you start with 3, then 5, then 7, 9, 11, 12, 13, and so on. So a pilot research study has been carried out, and we found that more or less after total number of grouping in each layer like 3, top 3, bottom 3, intermediate 3, total 9 groups are there. If you go beyond that, no much economy will be achieved. So a member grouping has to be done. Initially, I have assumed only one tube section for all thousands or whatever number of elements are there. Do the first cycle of analysis. Then we develop an Excel VBA code. This code, what it will do is, first it will isolate top layer member identification, bottom layer member identification, and web layer member identification. Then it will find out maximum tension and maximum compression in each layer. Then with respect to that, it split it into 3 groups. It split it into 3 groups based on forces. Okay. And so it's an iterative process. Then analysis, design, and optimum design will be carried out. So the cycle continues, I tell you. Say the first cycle is all members have same cross-sectional properties. Second cycle, each layer group is divided into 3 subgroups and assigned 3 different cross-sectional properties. So total 9 groups. Now a reanalysis was carried out and the iterative procedure was continued until the difference in weight of the space frame resulting from successive cycle was insignificant. This is a Formin code. This is diagonal on square grid. When you write this and run it in Formex, immediately this will be generated. Automatically it will be generated. Now, if this you wanted to generate in AutoCAD and MedasGen, it will take some time. Here you are very sure while writing all these things that what you intend will be generated. You did not to go and check everywhere whether the connection is proper or not, or whether the dimensions are proper or not. So that is why still people are doing the work for space frame structure in Formin. Then it has been through AutoCAD imported to MedasGen, and this is what the MedasGen, this is S4 condition. Total 9 elements are there, but only one element I'll assign initially. These are the diagonal on square grid, span length 30 meter, aspect ratio 1. It is a displacement contour, span to depth ratio is 16, and the support condition is S4. This is S4 support condition. That is 3 support at each corner. Similarly, this is the force contour of the same model. Then this is another one, square on square, displacement model S4. This is square on square. This is again square on square force model. This is square on square, aspect ratio 1, but support condition S1. This is S1. All 8 supports, all 8 nodes are supported. So this is displacement model, force model. Now what are the results means? See this. If you don't do the optimum design, then you will come out with this weight. It is in kilonewton of whatever space grid I have considered. But when I do optimization, then I am getting this weight. Now this is a very small one. So you see that almost 100 kilonewton difference is there in weight. The real space grids are much larger than this. So you can imagine that what gain you will take for after optimization in the weight. Now this is what the data which are ready for training neural network, like support type, span to depth ratio for each support type, what is the grid weight, optimum grid weight I am getting in kgf per meter square, what is the grid deflection in I am getting. These are the only things which is needed for neural network. These I have not touched. These I have just shown you that the top layer maximum tension is this, maximum compression is this. This is exactly divided into 3 groups. From base layer it is this, bottom layer it is this. S1, S2, S3, S4, and these are square on diagonal grid. This is diagonal on square grid, and so on. So with this background, now I am starting a neural network. The preliminary stage of the design process is identified with a high degree of uncertainty related to the design information and lack of clarity of design brief as to what is desired and what is possible. Now, those who really practice along with teaching for proof checking or in consulting areas in some offices, then only you will understand that whenever the architect gives you the planning, there is high degree of uncertainty related to design information. See, you don't know where to put the column, how to orient the column, what sort of grouping of column you wanted to do. You don't know whether you should go for slab beam system, post tension system, grid system, waffle slab system, flat slab system. So even you don't know whether you go or that is what is lack of clarity of design brief as to what is desired and what is possible. The development of computer supporting system in preliminary stage, many has started for one human computer system that try to automate the task of preliminary design stage. This has been suffering from a difficulty in computerizing the information and knowledge because it lacks formality of representation of designers' experience and intuition. See, even today I tell you, I work in computer-aided design since 1980s, I tell you. I have started working in StatPro environment in 1988. Then I worked with GT Strudel, I worked with Strap, CATS, then Struts, then Plan Menu, ETAPSAP, Midas Gen, and so on. I know that even I did interview with many of the experts in field. Even today, whatever may be the sophistication of the software packages, whatever may be the features available, a computer software, a machine cannot replace an expert. The reason is that most of the decision which for a particular project you have to take at the preliminary design stage or conceptual design stage. It has been proved by many research in Europe and US that whatever decision you take at preliminary design stage will decide 80 to 85% material resource requirement and labor resource requirement. So ultimately, 80 to 85% cost is being fixed. Ultimately, generally what you do, once you put column and beam and slab and floor framing system, which is generally for reinforced concrete building structure, what we are doing later on, we go on doing the design, still the design is same. So you are not doing what if analysis. You are not altering your scheme. Then it is not a efficient design. Whatever decision you have taken at the preliminary stage will reflect in the final design cost. Whereas the expert will put the design scheme in such a way that it will lead to economical design. So my point is, and many times expert only tell you that, oh, it's my gut feeling. This is what I felt when I have seen the architectural drawing that I should put this kind of scheme on this. It cannot explain it in terms of logics or mathematics. So for this kind of information, when this kind of information is there, your traditional one Newman computer architecture, even though it may be super. So that is what the point is. Now, what are the everyday computer system good at and not so good at? So it's a rule-based system, doing what the programmer wants them to do. If you want your software to do something, you have to program it, you have to write down everything, and then only you can run it. Whereas they are not so good at dealing with noisy data. Now, dealing with noisy data means what? That in real life structure, you may not have 100% surety about the quality of the data if it is being generated in field, a material being generated in field about the accuracy of the data. Then dealing with unknown environmental data, it is massive parallelism. Our is a sequential. It may be very fast, but one instruction is executed, then only the other instruction will be executed. But our brain will not work like that. It's a massively parallel. Then fault tolerance. See, fault tolerance is one of the aspects of massive parallelism. That indicates that if some links are being broken up, even though the program will work. Whereas in case of traditional computing language, it will never work. Then adapting to circumstances. That today you have written the code. After some time, if new data are available, then your code may not be compatible with that. Like in case of US, every 6 months they do some sort of amendment in their design code. So if you have written the Excel sheet or whatever code today, C++ for say design of a column or footing, after 6 months you have to do modification. Whereas if you have trained the network, then what you do is you do with some software design and then train the network. It will adapt the changing circumstances with a less effort than what effort you need to put to reprogramming it. So for such scenarios, and the real life scenarios are always like this, one has to go for artificial intelligence technique. It is the science and engineering of making intelligent machine. What is AI? Especially intelligent computer programs. It is related to the similar task of using computer to understand the human intelligence. Means AI is, I tell you, what you can say, an effort towards understanding how a human brain works. John McCarthy coined the phrase AI in 1956. Now there are 4 AI techniques: artificial neural network, fuzzy logic, genetic algorithm, and expert system. What is an artificial neural network? It is a computer program that can recognize patterns in a given collection of data and produce a model for that data. There is an input space, there is an output space. Like if you want to design, say, reinforced concrete column, input space are load, moment in two direction, material properties, end conditions, then whether it is short or long, and so on. And output space, dimensions of concrete column, reinforcement area, and distribution of the reinforcement. So that you need to map. That's a mapping can be done with neural network. It resembles brain in two respects. Knowledge is acquired by the network through a learning process. See how a human being learns. You always learn by trial and error. The very first thing we learn is how to walk. Thousands of times we topple up, but then we understand how to make balance. So it's a trial and error. There are no rules that you have to do this way and that way. And the second thing is that the interneuron connection strands, known as synaptic weights, are used to store the knowledge. So the weights are storing the knowledge. And there are number of trillions of interconnecting neuronal weights, synaptic weights. So that is why it is a huge, massive parallelism. So artificial neural networks are an attempt to harness the massively parallel distributed computation of biological brains for a variety of purposes. Computer technology is rapidly approaching the processing power of human brains, but still the organization and function of the human brain is a huge unknown. Biological brain use neurons that are 10 raised to 5 to 10 raised to 6 times slower than our silicon logic gate. Yet they perform computations better and faster than our best computational algorithms. Like one is face recognition, or the second thing is that say before the Second World War, American Air Force, they lost many airplanes due to sudden crash in fighter plane sudden crash in air. Actually, they put the silicon logic gates, computer, hardware, and software inside, which collects data and then process it and then give the solution to the pilot. But the plane is traveling at such a huge speed in space. Before the computer do some computation in those times and give some viable option to the pilot, the plane crashes in the midair. They found that when pilot has taken decision by themselves without looking to the computer, without waiting for the computer response, the many crashes have been saved. That means the human brain works faster than best silicon logic gates even today. Now, why are ANN applicable in engineering? There are two things. It is able to map causal model. Causal model means mapping from cause to effect. That is for estimation and prediction, our design, analysis. And inverse mapping, that is mapping from effect to possible cause. That is for detecting the damage. Damage detection and preliminary design. These two are the area in structural engineering in which neural network, either along with genetic algorithm or along with fuzzy logic, make a very fantastic tool, a research tool. Now, engineers often deal with incomplete and noisy data, which is one area where ANNs are most applicable. This is particularly the situation at the preliminary stage of the design process. Now, where neural network application, function approximation, time series prediction, classification, data mining. What is neural? Say, a human nervous system is built of cell called neuron. This is one neuron. This is another neuron. Each neuron can receive, process, and transmit electrochemical signal as it is shown over here. Dendrites, these are dendrites. These dendrites extend from the cell body to other neurons, and the connection point is called synapse. This is synapse. This is the dendrite of this neuron. This is the dendrite of this neuron, and the connection strand is known as synapse. Signals received among dendrites and transferred to and some in the cell body. Mean through this synapse, whatever signal will be transferred from this first cell body to axon, axon to dendrite, dendrite to synapse, other dendrite, then axon to other cell body. If then cumulative excitation exceeds the threshold, the cell fires, which sends a signal down the axon to other neurons. What is the difference between traditional programming and neural computing? Say it follows rules, whereas it learns from data. The solution formally specifiable. Here, you know what is mathematics. Here, rules are not visible. How it interconnects, how it maps input to output. It cannot generalize. It is able to generalize. It is not error tolerant, whereas it is copes with noise. Now see, in one case, just I'll explain only one aspect, cannot generalize and able to generalize. Suppose we have written a code for Indian code, IS 456, 2001, 893 and 2016 for reinforced concrete design. Now it cannot work for British code or American code. But suppose we have developed a neural network for Indian code. Now the same network you fine tune for British code, you again retrain a little bit with data generated using British code, and then you use it. So here that is generalization. It can be used for different code also. It generalized means it is a design box. Now whether Indian code, British code, American code, you can develop the things. Even you can develop the things in such a way that network 1 will work for Indian code, 2 will work for American code. You give same data and it will give you the results for the different codes. Now, what are the characteristics of neural network? So it is learning from experience, generalizing from examples, developing solutions faster and with less reliance on the domain experts, a computational efficiency, and highly nonlinearity it will capture. I will show you. Now, the strength of the neural network is its power, that it will model the complex function, nonlinearity built into the network. Then ease of use. It learns by example. Very little user domain specific expertise is needed. Only you need is data. You don't need expert of the structural design field to develop a excellent neural network. Only thing is that you need a quality data. Then intuitively appealing based on model of biology, will it lead to genuinely intelligent computers or robots? So now this thing you keep in mind very clearly, that neural network cannot do anything that cannot be done using traditional computing technique. But they can do something which would otherwise be very, very difficult. When we can't formulate an algorithmic solution, when should you go for neural network? So when we can't formulate an algorithmic solution, when we can get a lot of examples of behavior, we require learning from experience, when we need to pick out the structure from existing data. Now this is what a simple neuron, where these are the input signals or signals from a previous layer. These are the weights, synaptic weights. Weighted sum will take place through some activation function like logistic or 10 hyperbolic in case of the big propagation. It will, you can transfer the, just a minute, call is there from my college. Hello. સાહેબ હું અત્યારે એક એક્સપર્ટ લેક્ચરમાં છું. એક્સપર્ટ લેક્ચરમાં છું NIT શ્રીનગર. હા, આર્ટિફિશિયલ ન્યુરલ નેટવર્ક એ 1 વાગ્યા પછી પતશે. 1 વાગ્યા પછી ઓકે. Sorry for interruption. Now, say this is the generally 2 activation function: logistic function, that is sigmoid, and 10 hyperbolic, generally using structural engineering. Now, generally it is termed as squashing function, because what will happen, that whatever inputs you are giving through this weight, it sums. That might be negative infinity to positive infinity. But when you pass it through this, it squashes between 0 and 1. So this is the nature, between 0 and 1. Lambda is, it is 1 upon 1 plus e raised to minus lambda into xj, where xj is the what you are passing through this function. And lambda is the slope of this function. And it squashes between 0 and 1. It's saturated at very large and very small values. Then 10 hyperbolic function, domain is -1 to +1. It is between -1 to +1. These two are generally used for vector propagation. And this is used for radial basis function, Gaussian elimination. This is globally very excellent. This is locally very excellent. Now this is multi-layer feed-forward network, input layer, hidden layers, and output layers. These 2 layers are connected with environment, and these are the hidden networks, hidden layers. How do neural network work? So what you have, so suppose I am having a 700 data. In 700 data, what I am having, what is the span length, what is the span to depth ratio, size, what is the end is the deflection, and what is the total tonnage weight of double layer grids. Such 700 training pairs I am having. Okay, so these are the pairs 1, 2, 3, and so on. Then present the data to the network. Network computes an output over here. It's a supervised learning. There is a teacher. I know network output compare with the desired output. Then you find out the error function. You formulate some error function and find out the error. That error is back propagated to the network in such a way that the weights are being updated. So this you continue till you get desired accuracy. Then what is the use of network? Present the new data, that is testing data, unseen data. Network computes an output based on training. At that time, the weights are being freeze. So this is the whole process that you start here, select a neural network multi-layer perceptron. That means you have to decide how many nodes are there in input layer, how many nodes are there in output layer, what are the number of hidden layer, 1, 2, maximum 2, not you should never go beyond 2. What is the number of neurons in each hidden layer? This is all MLP, that structure you have to select. Assign random initial values for all weight parameters. Initially, you have to randomize the weights. Then perform feed-forward computation for all the samples in the validation set. Evaluate the validation error. If desired accuracy is achieved, then stop training, freeze the weight, check the testing. If not, then perform feed-forward computation for all samples in training set. Again, evaluate the training, compute the derivative of the training with respect to ANN using wave propagation, update the neural network weight by using any gradient descent algorithms, and again find out the validation error, and so on. Now here, learning in neural network is knowledge is represented in neural network by the strength of synaptic connection between neurons, that is connectionism. Learning in neural network is accomplished by adjusting the synaptic strength. There are three primary categories: supervised, which is what I have explained you. Then reinforcement, that you have to only signal good or bad training signal. Means whatever answer is there, whether it is a good answer or bad answer, that only you have to tell. You have not to tell the exact desired answer. And unsupervised training. So by itself, Kohanen, by itself, there is no training signal. It is self-organizing map, clustering process. So what we are doing right now is only this supervised learning. Now this is all mathematics, how it is being, what are the equations which are to be used, but I'm not going into that detail. This is what, say, initially your point will be over here, and this is a error surface which is being generated through weight updates. You have to move to the point where minimum error is there. These are the weights. There are a number of weights. No? There is only 2 weights and errors. So this is what you can say. Now there are, say, what happens that what are the stopping criteria? Stopping criteria is one is that you have to stop at maximum number of epochs. Epoch means, suppose I am having 700 pairs, out of which for 60 to 65% I keep it for training. 10% I will keep it for cross validation, and 20% to 25% I will keep it for testing. So one epoch means, suppose 500 I keep it for training, then 500 training set, when I give once, it is one epoch. Like 1,000 of epochs you have to run. So you have to decide number of epochs. Because sometimes when it trap in local minima or network paralysis took place, there is no sense in going lakhs of epochs. So that is why you have to put stopping criteria as number of epochs. Then the second one is mean square error on training set. And the third is stop when overfitting is observed. That is, when training data is being memorized. An indication of overfitting is when the cross-validation error is the average cross-validation error plus standard deviation of the cross-validation. What will happen? That when you go for neural network training, during training you are updating the weight. So it always goes on decreasing, always goes on decreasing because it is gradient descent and you are updating the weight. But during that training, you are giving cross-validation and you are not updating the weights. So it goes up to certain epochs. Then after that, the cross-validation errors start increasing. The cross-validation errors start increasing. That means you have to stop it here. Again, you have to retrain. So that is what is called a cross-validation. Now, what are the performance issues in neural network backpropagation? Model accuracy, coding of input values, like how I will code S1, S2, S3, S4, support condition, I'll show you. Data scaling, weight initialization, learning rate and momentum, optimization method, and the architecture selection, that is number of hidden layer and number of hidden nodes in each hidden layer. This is generally what are the common problems with backpropagation net? Slow training and sensitivity to initial set of network weights. You see here, training trap in local minima or non-guided design of an optimal network configuration for adequate generalization. This is very, very important to understand. So here, underfit, overfit, and proper generalization. Ideal should be like this, that has been shown over here. When you want to develop a neural network, some expert person initially is required to help you because there are no guided rules even today. If I want to design artificial neural network for actually loaded short column, long column, biaxially loaded column, footing, no guidelines are available how to start. So that is why some expert is required because it is a not guided design tool. Now these are some of the efficient learning algorithm to update the weights, that is delta bar delta, quick prop, Leeuwenburg Marquardt, and so on. Another one is radial basis function. Now just I will brief and then I'll show you the results. See, the idea of the radial basis function is that it derives from the theory of function approximation. We have already seen how multi-layer perceptron network with a hidden layer of sigmoidal unit can learn to approximate function. Actually, multi-layer perceptron is also, it's a function approximation, but the way in which it does the function approximation and the way in which radial basis function does, these two are different. RFB network take a slightly different approach. Now, what are the main features of RFB? They are two-layer feed-forward network. I'll show you. The hidden nodes implement a set of radial basis, that is Gaussian function, rather than sigmoid or tan hyperbolic. Output node implement again linear summation of function as in MLP. But here there are two different training phase. The new network training is divided into two stages. First, the weights from the input to the hidden layer are determined, and then the weights from the hidden layer to the output layer. Whereas in case of backpropagation MLP, all the weights are updated simultaneously. Here first between input layer to hidden layer weights are updated, and then the hidden layer and output layer are updated. Here the training and learning is faster than MLP, and the networks are very good at interpolation. Like here. So suppose this is a function which I wanted to simulate. Then these are the all Gaussian what you can function approximation function, squashing or transfer function I am using for radial basis function. What are important thing is the placement of the localized Gaussian. This is one I have put, second I put like this, third I put. Then the control of width of each Gaussian. Then the setting of amplitude of each Gaussian. If we can accomplish these three tasks, we can approximate any arbitrary continuous function with radial basis network. Now, this is how what you have to train is this, and then you have to train this. And here, these are this kind of function. So that is what the point is. So this is generally termed as pattern layer rather than hidden layer in case of RFB. This is how MLP generalized the function, and this is how RFB generalized the function. This is how, these are the main comparative points. Where this is RFB, it will do the localization over here, whereas it will do the globalization over here. So RFB require more hidden units than MLP. Then RFB units cover a small area of input space. MLP unit cover a larger area like this, whereas this is smaller area. MLP generalizes better. RFB locally more accurate. RFB decision rules can be written. If you want to go for rule-based neural network, how neural network has taken this decision, if you want to know that, then you should go for radial basis function. Then it is training much faster. This requires far more exemplar to reach accuracy comparable to MLP. Here, more data are required than this. Now, I am showing you my neural network simulation results. This is my input grid, means grid span, grid depth, and grid support condition. These three parameters are input. I'll normalize it, then I'll give it to a neural network, then I'll do the post-processing over here, and then I'll generate the output. It may be weight, deflection, or member forces, anything. Member forces analysis, weight and deflection design. I am showing you weight and deflection over here. So these are the input data, like span. Then support condition, I adopted this scheme. Like I taken 4 nodes, and if this node is 1 and the rest is 0, then it is S1 I call. Similarly for S2, 1 is on and the rest are 0. Similarly for S3, 1 and the rest are 0. And S4, 1 and rest are 0. And grid depth and grid weight. And my output will be the, and grid depth. These are the inputs, Span, support condition, and grid depth. And output is weight and deflection. So this is output. So this is the grid weight output. This is 2 hidden layer I have taken. So in this input layer, 6 nodes are there: span, support condition, grid depth. This is a bias one. And then the hidden layer 1, hidden layer 2. I'm not going to detail because there is no much time now, because I have to give some time for question answer also. And grid weight. I use Neuro Dimension developed by NeuroSolution. It is a very fantastic tool to develop neural network application. I use NeuroSolution from Neuro Dimension, American-based company, Neuro Dimension, Florida-based company. They develop AI-based tool. So that is a breadboard. This is also a breadboard. Then see the results are there. That what is the grid weight desired? 19.94 kg per meter square. And my network is firing 9.98. What here I desire? 14.27. And the network fire 15.82. This is percentage error in big propagation. Similarly, this is the weight fired by radial basis function. So here I need 34.75 and it is giving me 36.42. I need 15.78 and it is giving me 14.28. So this is the percentage error by big propagation, percentage error by radial basis function. Similarly, this is training. Now this is more important, testing, because during training you are fine-tuning the weight, so you will bound to get less error. But during testing, if you get error within a bound of 10% plus and minus, that is a good one, because the weights are freeze. You are not changing the weights. So here, during training, say 30 meter span, S1 support type, depth is 1.36 meter, my grid weight is 18.09, predicted by, desired. This is from MIDAS I am getting. Predicted by neural network is 17.31, so the error is 4.29%. And predicted by radial basis function is 16.86, the error is 6.8, and so on. So this is what, again, the weights for another kind of thing. This is square on diagonal. This is diagonal on diagonal. 5 type of grids I have taken. This is diagonal on square. Deflection now. See again, I need 28.8 mm and the network BP back propagation MLP 29.76, radial basis function 29.18. So this is, you see what in non-linearity it captures. See the non-linearity during training. This pink color gives grid weight desired and green neural network fire. So how you see, and during testing, this is for weight, this is for square on larger square, this is on square, square on larger square, square on diagonal, diagonal on square, diagonal on diagonal. Then this is with radial basis function, same thing. You see the error by back propagation and by radial basis function. It is bounded by negative positive 10% error for SOS. Then again, this is for during training, this is during testing, aspect ratio 1, and this is grid weight, and so. Then this is grid deflection, that was, and for grid deflection also again you see how it matches. This is another way how I represent error. This is all. Now, if you want to check the performance, one is mean square error, but the second one, because it will give you the, what you can say, how well the network output fits the desired output. But whether in same direction, in the direction of the desired data, the network data is also firing. So that if you want to check, MSE will not give any clue to that. So there is another correlation coefficient that R, which is, this is X, what is network firing, and D, what is desired. If correlation coefficient generally is between -1 and 1, generally you can say that the data is moving in the same direction if it is between positive 0 and 1. If it is -1 and 1, it is another direction. That should not be adopted. Again, in our case, if it is more than 0.9, then you can say that your network is ready for deployment. Now this is, say, for square on square grid, I have taken 64 training pair, 10 testing pair. In input node, 6 nodes are there in input layer, 2 hidden layer I have taken. My base network is 4 node in hidden layer number 1, 4 node in hidden layer number 2, 1 node in output layer, that is weight. What is training MSE? This. What is cross validation MSE? This. What is correlation coefficient? You see 0.9, 0.98. This is an excellent result. Now that can be used for deployment, for unknown testing purpose, for real life structures. Now SOS, I got Leonberg-Marquardt algorithm gives you my best result. Percentage training error for training absolute maximum is this, testing is this, and percentage error, this is absolute maximum, this is during training, and this is testing error, this is during, and this is activation function. So here, this 10 hyperbolic gives always the best result. So what I did is, I have trained the network like first I'll take only one hidden layer. I'll change the number of nodes. There are certain rules given in computer science that depending on complexity of the problems, with what you start, like 2, 3, up to how you should go. But there are no hard and fast rigid rules. It is flexible one. It is problem dependent. Then I have started with one hidden layer. I found that I am not getting a good result. Then I have started with 2 hidden layer. Then in each hidden layer, I started from 3 nodes to 9 nodes in each layer, and then so many permutation and combination I got, out of which these I am getting the best one. Then what you can say, learning algorithms like conjugate gradient descent, then that is conjugate gradient, delta bar delta, Liebenberg Marquardt, momentum, quick prop, and so on. And whichever gives me best result, that I have shown over here. So these are for backpropagation net. This is for what you can say RBF net. In which case, I have taken one is pattern layer. Pattern layer, you see, I have told you now, many nodes are required. This is Gaussian one. Then there is one hidden layer also I have taken. So that I have taken 4 nodes over there. So these are the topologies. And these are all means we have discussed now, whatever are there. Only thing is that there are 2 things which I wanted to let you know is, what is the obstacle to fuller implementation of neural network tools? Even you won't find much tools in use today. Most reported ANN-based studies, although successful, have not been applied in practice because engineers have doubt about their use. This is mainly due to the limited theory to assist in their design, no guarantee of success in finding an acceptable solution during training, and a limited ability to rationalize the solution provided. People treat it as a black box, means you are giving some number, you are getting some number as output. How it has been given, nobody knows. So that is why, that is the biggest problem. How you overcome this? So overall, despite the limitations of ANN, they have a number of significant benefits that can make a powerful and a practical tool for solving many problems in the field of structural engineering. Applied appropriately, neural networks are certainly the key technology for future intelligent civil engineering structures. These are all conclusions and other things I have shown you. And what are the journals which I have reviewed when I did my research? This I have enlisted over here. Okay. So these are, thank you so much. And now if you have any query, I am here to solve the queries. Means.
Thank you so much, sir, for explaining all the basics so well. We are extremely grateful to you for sharing your knowledge with us. And I guess we will wait for some time for the questions. If anyone has any questions, she can just write it down in the chat box, and I will send them to sir or ask on your behalf.
So this is a very fascinating tool. Only thing is that once you have quality data, because quality of the data is very, very important. And this is not the platform also, neither platform nor time is there to discuss that, what I mean by quality of data. But neural network, you can even develop the network from experimental data. This is very important, I tell you, because many of the research which is being going on in US and Europe in the laboratories in the field of concrete structures, I know, high-rise, they are unable to put it in terms of codal provision. They only have data that if such is the input, that should be the output. In such cases, no software vendor is possible for no software vendor to possible to develop any tool for from that data. So there only neural fuzzy will work in such cases.
I guess all the basics that you explained so well, there aren't any queries or questions from the participants' side. Thank you so much, sir. We are really indebted to you for sharing your knowledge with us, and we are hoping that we will be having many more sessions with you in future. Thank you so much. Okay,
somebody has
just
written. No,
yes, sir. Yes, sir. We have a question from Laran Satapathy. He's asking that could you please explain in what other way we can use the application of neural networks in structural system except strength monitoring?
See, a neural network, generally being used in structural engineering in two areas only. It's a preliminary or conceptual design scheme. Even let me tell you that peoples are forecasting rather estimating, not forecasting, estimating the final cost of the project. People are now trying to do that with neural network. That whether it is possible to come up with some idea of how much costs get involved in this project with neural network for building structures. People have started working in that area. Another area people have started working in the what you can say performance-based seismic design. That is seismic risk evaluation. That people as I did in case of AA space grid, people do direct displacement based design, performance based seismic design, and then find out the vulnerability index and then train the neural network to get the damage index or vulnerability index. We have also started working in that area for neural network. So one is seismic area in which damage prediction of the damage index or vulnerability index, that is seismic assessment. That's a very big area. Recently, area open up for neural network and preliminary area and damage detection. Lot of work has been done in the area of damage detection.
Thank you so much, sir. Another question is from Maz Naeem. He is interested in knowing that how can he get started with learning artificial intelligence, and if you could suggest some resources.
Ma'am, I tell you, it's all my what you can say curiousness. Nobody said me anything. So I share one thing. How we do research means. So there are two kind of research. One is a qualitative research and one is a quantitative research. I worked a lot 6 years under Dr. Abhijit Mukherjee at IIT Bombay. So he told me that I give you architectural plan, and if you can put the if you can develop a rule-based neural network and decide the column position, column grouping, beam position, beam grouping, then I'll give you the PhD.
Okay.
Another PhD means that you have to develop lot of data, do statistical analysis, find out something from that data. So it's one is a intelligence driven, where very few people are knowing at that time. Nobody knows about that and all those things. Even I tell you, IIT, even Stanford has given PhD for developing neural network application for design of slab and beam in 1990s. Whereas now my students are doing much more than that. So, but that is at that time nobody knows that. Now, the question is that how I get connected, it is due to Abhijit Mukherjee. And once I understood that this is something very fascinating, then I started learning at my own. So I know that how nature works. I tell you one secret. In my life, I have seen that if you have really intention to learn something, the nature automatically provide all the resources to you. It is unknown, but it automatically happens.
It's a very valuable suggestion, sir. And yeah, you're absolutely correct. You should have the interest before starting anything, and obviously you will start making your own way whenever you have that intention and determination to learn something.
Yeah.
Thank you so much, sir. Thank you so much. We are really,
thank you. And thank you so much for listening me very silently.
Thank you so much, sir. We are hoping that we will have many more sessions with you in the future so that you can share your valuable knowledge with us. And thank you so much again for being here and taking out time from your busy schedule for this session.
Okay, thank you so much, Sakiba. Thank you.
Thank you, sir.
Bye.
And to all the participants, we will be having 2 more sessions tomorrow. The links of those sessions will be sent to your emails. And thank you so much for being so interactive with the speakers and being nice to follow all the rules. Here we will have a wrap for today's session. Hopefully, we will see you tomorrow at 9:30. The links and all the details will be sent to your mails along with the feedback forms. We are sure that you will give us your valuable feedback.
Sakiba,
Yes, sir.
again,
Yes, sir.
you requested sir to share their presentations.
So he has left the meeting. I was
Okay,
about to tell him, but you can mail him and ask
Okay.
for the same.
Okay. Yes.
Okay, so thank you, everyone. Thank you for this session. And we will send you the feedback links and hopefully you will give us your feedbacks. Thank you so much.
There's a request, ma'am. There's a request. I am Rajesh Kashyap.
Yes, sir.
Please write the name of the topic also, because there's so many mail coming in the same reply cluster of mail is there. So to decide which link is other, slightly it is confusing. If you can just name the topic above the link which you are giving, first thing. Second, my request is, ma'am, like, there are a lot of people who are professional. Like I'm still in the office, and in between we are listening to this lecture, and we have to sit down again in the afternoon and the night, go through the complete lecture. Actually, if you want to do justice to this topic, this feedback form which you are giving, you are closing it at 6 o'clock. It is slightly
So you want,
flexible.
I got it. You want the link to be open for a longer period of time,
Longer period can be in night 2 o'clock or 3 o'clock, because if one reaches home by 8 o'clock or 9 o'clock, we can only sit after 12, ma'am.
Okay, so no issues. We will just work on that. Actually,
Sakiba? Yeah, we can keep the link open till 12 a.m. It's not possible to keep it till 3 a.m. because that means somebody will have to be awake at that time and then close the link. So we'll make it available till 12 a.m. I think that will be fine with everyone.
I think we can keep it till the morning of the next day. I think at 9.
Right, ma'am.
9, because he's saying that he has to go through the lecture again because he's
fine.
busy.
So we'll be closing the link tomorrow morning.
Yeah, tomorrow.
Right.
We'll open the link for next day, up to the morning of the next. Okay, is it fine, sir?
Thank you, ma'am.
Rajesh?
Thank you. Yes,
And
thank you.
regarding the links you are saying, we try our best to like put the description inside the mail. There will be the description that what the link is about. So even if you are having any confusions, we will just change the subject of all the mails that we are sending. Okay.
Right. That's nice, ma'am.
Anything else? Everyone is fine. Any queries other than this? I don't think anyone has any queries. Thank you so much. Thank you, everyone. We'll be joining you all tomorrow at 9:30.
Nice